I am not able to record it. Okay. More. Record in the cloud. Okay. Okay. So now, you have this action principle. Okay. So you have action principle in mechanics. And here we have action is equal to integral some quantity called the Lagrangian times dt, where Lagrangian in general depends on position dot and t. And this is from 1 to 2. And the equations of motion obey delta S is equal to 0. Delta being the variation of different paths. This you are familiar with, right?
Yes.
Okay. What about others?
Yes.
Okay. Now, so basically it means that if I have a 0.1 and a 0.2, and I have various paths, suppose I have a path, okay, and then I have various paths. It can be anything. Along all these paths, I calculate this integral. And particles follow that path for which S is equal to extremum. Yeah, I mean, actually, I'm just because since it's not in classical mechanics, there are beautiful, many number of subtleties in this whole thing. Okay, so maybe if people are still interested and they are later at a later date, I will come to this also after we have finished the GR course. Okay, so this gives the equation of motion. Okay. Now, for a free particle, okay, so now what are the things which are there? Here, basically what I need is that this quantity has to be a scalar. This Lagrangian has to be a scalar quantity. Okay, that is the... So now, scalar, depending on the transformation, suppose Lorentz scalar or Newtonian or, like if I'm doing relativistic, it should be Lorentz scalar, for example. So now suppose I have S is equal to minus alpha integral point A to point B times ds. What was ds? ds is equal to dt square minus dx vector square for Minkowski, and ds square is equal to gij dxi dxj for any general spacetime. For the case of Minkowski, gij becomes eta ij and it reduces to the previous expression. You understand this?
Yes.
Okay. Now, if suppose I have a free particle, the only scalar I can construct out of it is ds, because there's nothing else in the universe with which I can actually construct any other scalar. Okay, ds is the only thing I can construct. Is this clear?
Yeah.
The only thing available with me is space-time. And this is the only thing I... And so I can actually now write it in... So, okay, for the case of Minkowski, we have S is equal to minus alpha integral dt square minus dx square root. Okay. That is, as the particle goes from point A to point B, I calculate all the ds's in between. And this is equal to minus alpha times integral dt square root of 1 minus dx square by dt square, which is equal to minus alpha integral dt square root of 1 minus v square, the famous 1 minus v square expression. Now, okay, so now this is the thing. Now remember that here we have taken c equal to 1. Now if you compare this, so I have s is equal to minus alpha integral dt 1 minus v square. Now, the fact that this action is to be minimized instead of the form is independent of whether it is Newtonian or relativistic. What dictates Newtonian or relativistic is a form of capital L. Is this clear?
Yes.
Okay. So now if I compare these two, I get for special relativistic mechanics, L is equal to minus alpha square root of 1 minus v square. Okay. And now, let me now play around with this. I know that for... okay. So for... Okay. So now I will consider for the case of non-relativistic limit, I have v much less than 1. And this implies L is equal to minus alpha 1 minus half v square. I mean, you already see a kind of something familiar emerging. Do you see what is familiar here?
Yeah, also being M.
That is okay, but something more familiar. It's a kinetic energy kind of a thing which is there. So this is equal to minus alpha plus half alpha v square. Okay. Now, non-relativistic equal to half mv square. But you can always add a constant to the Lagrangian. It will not change the equations of motion. Okay? Right? Because you are actually getting the equation of motion by varying it. So a constant will remain a constant. It's like differentiating a constant. Okay? And so this implies that alpha equal to the mass. Hence, the Lagrangian is equal to minus m square root of 1 minus v square. Okay. So this is my Lagrangian for relativistic particles. Is that okay?
Yes.
Yes.
Okay. Now, see, as far as now, the fact that delta S is equal to 0 implies del L by del X I is equal to d by dt of del L by del xi dot is general, not to do with relativistic or otherwise. Okay. And relativistic or non-relativistic or relativistic will decide only the form of L. But once the L is given, this is a common thing. And so if I use these two, what will I get? I will get 0 is equal to d by dt of del minus m square root of 1 minus v square by del vi, right? X dot. And so this implies that d by dt of, okay, so this will be 1 by 1 minus v square 3 by 2 with a minus half and a minus v and a minus m equal to 0. Is that okay?
Yes.
Yeah.
Why 1 by v square whole power 3 by 2? Shouldn't it be 1 by 2?
Oh, yeah. Sorry, you're right. I was actually calculating something else. And I had a 1 by 1 minus v square by 2. So in that memory, I just put it there. So it should be plus. Right? It's okay, now?
Yeah.
Okay. Then it is okay. You're right. Yeah. I was wondering why. Okay. And so this implies that d by dt of m v by square root of 1 minus v square equal to 0. And this quantity mv by square root of 1 minus v square is the relativistic momentum. And it says that d by dt of momentum is 0 for a free particle, which is what you expect. Okay?
Yeah.
Okay. And now you can actually see another thing here. This is equal to what? This is equal to P is equal to M gamma V. And we already saw that M gamma V is basically the four velocities, this M into four velocities spatial component. See, U alpha was gamma times V alpha.
Yeah.
Right? You remember, right? So you had U0 is equal to gamma, U alpha. So you are seeing everything matches now. Everything ties up very well. Okay, so this is to do with yeah. So this is momentum dp by dt Yeah. Okay. Okay. Now, let us now go further. We will now go to, you see, because initially I was thinking of doing the electrodynamics in this way, but it will just take us too far away. It will go into the action principle for electrodynamics, and I don't want to do that because that will take us completely away from it. See, what happens is when I teach general relativity over here, I mean, they have completely done a course on a formal special relativistic electrodynamics. So I just start with the tensors and do it. So, I mean, I'm just trying to make up for that gap. Okay. So we saw four velocity, we had four acceleration. This was ui, this was vi. We have similarly four momentum, this one. Now, when you want to do electrodynamics, so what I will do is, in this one, I will not prove everything. I will just mention at various points how things are, and with the aim to use it finally in GTR. Okay. So we do electrodynamics, and the first quantity we have here is called four potential. Okay. We know that in non-relativistic electrodynamics, we have a scalar potential, and you call it scalar because in non-relativist electrodynamics, we are considering transformations of three-dimensional space, namely rotation and translation. And with respect to this potential is invariant, and that is my phi. And then we have vector potential, which is a vector, which transforms as a vector in three-dimensional transformations of rotation and translation. Okay. Now, just like we have, okay, so we can define a quantity which is a four potential such that A0 is equal to phi and A alpha, A alpha is equal to the alpha component of this, okay, of 3D. Okay, so this is called the four potential, and just wondering whether I should, so I'll just mention this, and yes, this whole set of interesting things about four potential, but I will, okay. Okay, so this is there. Then I will talk about gauge invariance. In three-dimensional, when you do gauge invariance, we say that phi goes to phi prime defined as phi minus del f by del t. I'm taking c equal to 1. And vector potential A goes to vector potential A prime given by the original vector potential plus gradient of f. You remember this, the gauge invariance, gauge transformation. You
Yes.
come across this, right?
Yeah.
Yes, yes.
Okay. Now, what I do is, I define my gauge transformation in 4D as AI goes to AI prime defined as AI minus del F by del X I. Sorry. No, sorry. Here I should be careful. Here I should be very careful. It may not matter in special relativity, but I want to keep it, okay, because it will matter in GTR. Okay. Now, if I take xi as x0 as t and xx as x alpha, then I will get back my previous thing here. Is this okay?
Yes.
So, for example, then I have A0 going to A0 prime equal to A0 minus del F by del T. And here you have to be careful. A alpha goes to A alpha prime is equal to A alpha minus del F by del X alpha. Now what I do is I write A beta is equal to, okay, so I now raise this one. So I have A alpha is equal to minus A alpha in Minkowski. Right? That is eta ij. Because the spatial portions have a minus sign. You remember I mentioned it last time.
Yeah.
So this and this gives me A alpha is equal, goes to A alpha prime given by A alpha plus del F by del X alpha. I mean, it will become minus everywhere and the minus will cancel out. So this will be the thing. And I get back the gauge invariance equation. We have gauge transformation equation. Okay?
Yes.
Okay. Now, let me just, because I want to come fast to the Maxwell's equation in relativity so that I can start using it in my right-hand side of Einstein equation in GTR. Okay. Now, I can define an electromagnetic field tensor Fij. And I define my Fij as del by del xj ai minus del by del xi aj, which I can write it as, in fact, that soon I will be using that notation in track 1. I write it as ai comma j minus aj comma I. Comma indicates partial derivative. That is ai comma j is equal to a del I by del xj. Okay, so this is my Fij. And okay. Okay, let's just give you the results. Now, suppose if I have the action for a charged particle in electromagnetic field. Then this action is given by S is equal to one portion is my standard action, which is integral minus m ds, which we saw earlier. The action, the additional action for interaction, what we can write it as the charge. See, the charge is the parameter which defines how much interaction is there from the particle side, and AI measures the parameter of the field. So now suppose I write an action of this kind. Now you can ask, how did I write this action? The answer is that you start motivating it by saying that you want to write the simplest form of the action. So the simplest form of the interaction part of the action is charge and this gauge field. But this is not a proof. The only proof for an action is that finally, when you get the equations of motion, do they match your observed experimental result? Okay, so that is the ultimate truth. It turns out that this does give, as we just see. Now, if I now vary action S is equal to 0, now I can write this as the following way. This I can write it as minus m square root of 1 minus v square, the way I did earlier, ds minus integral ai sorry, this is dt. Okay, ai dxi by dt. Is this okay?
Yes.
Yeah.
This is equal to minus m square root of 1 minus v square 1 minus v square minus e a0 dx0 by dt is 1. Okay, dt plus, sorry, I'll put it as minus e a alpha v alpha, and I will take this dt out common. Is this okay? Because I have dx0 is equal to dt and dx alpha is equal to v alpha dt. Is this expression okay?
Yes.
Okay, fine. And now, if I compare it with S is equal to integral L dt, so I will have del L by del x I, okay, del L by del x0 will be equal to, there is no x over here, there is no time dependence over here, so I will have only minus e a0 dot minus e A alpha dot V alpha. Okay. Now remember that we are still deriving the equation of motion. In this, V and X are independent variables. Only after you have defined a trajectory, after getting the equations of motion, the particle chooses a particular velocity. So as far as the Lagrangian is concerned, velocity and position are independent variables. That is, at every point, I can possibly have any velocity because I am allowing all paths to take before deciding which path it will take. Is the logic clear?
Yeah.
Hey, what about others?
Yes,
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 yes.
yes.
Okay. Okay, so this is there. And then I will have del X alpha, sorry. Del B alpha. Okay, so fine. So del by del T. Okay, and then I'll have del L by del X alpha will be equal to, again, there is no X dependence here. And so I will have minus E gradient of A0. Okay. Let me be careful here. See, here alpha is a dummy variable, right? So this alpha is independent of the other alpha. I mean, do you get this? You see, this is a dummy variable. So I should use, let me use a different thing here because for every alpha here, every possible alphas are allowed here. So I will write this as beta beta. Okay. And so this will be this minus E del alpha A beta, I mean here also, A beta V beta. Okay. And further, I will have d by dt of del L by del X alpha dot, I can calculate. And then I will write my equations of motion as the spatial part as del X by del X alpha equal to minus, now this is what del alpha A naught is basically minus E alpha component of gradient phi, because A0 is phi. Is that all right? See, I told that A0 is the zeroth component of the potential, which is phi. I mean, here I had this. Here. Okay. And, okay, and then minus, now if I want to write it as a vector potential, then this vector potential is an upper one. So this will be plus E del by del X alpha A beta VB. Is that okay? अरे बताओ यार.
Yeah. V beta is a constant, right?
Which one?
V beta.
Yeah, because I told you now that at the
Yeah,
level
yeah.
of Lagrangian, velocity and q and x are independent variables.
Okay, okay. I'm just making sure.
Okay. No, I will actually, this, why this is an independent variable is very interesting insight. I will come to it separately because it's a completely mechanics thing. And in my class on classical mechanics, I actually spent half a class just to explain this. Okay. I will come to this, but right now you take that. See, okay, let me tell you this way. You see, you consider a large, desert, and you put a coordinate system here. Given a point in x, it can have any value of v. Given a point x, any value of v. But now suppose a lorry has passed through this and makes a track. Then along the track, for a given value of x, there is a given value of y. It means the track is defined by a certain function y as a function of x. Otherwise, for an arbitrary point in the desert, in general, the truck could have passed this. So for the same x, there could be another y. Could have passed this. For same x, another y. So x and y are independent. Similarly, once you have specified the path taken by the particle, then along the path, you know what corresponding to x, what is velocity. But at the level of Lagrangian, I have not committed myself to which path I am taking. I am considering all paths and finding out that path for which action is minimum. Since I am considering all possible paths to check which action is minimum, in the Lagrangian as such, the velocity and coordinate are independent variables. Do you understand the analogy?
Yes, yes.
Yeah, yeah.
So this is a very deep reason why, generally all these Goldstein will write in one sentence, say velocity and potential and position are independent. But this is the fundamental crux of why it is. And this has got a very deep-rooted thing. When you do central force motion, there is a slightly different way if you do it, then you'll get an opposite sign. I'll come to it sometime. Okay. But it has all to do with that basic thing that you cannot use the result of the equation of motion in the Lagrangian. Because at the level of Lagrangian, the velocity has the trajectory, the particle has not committed itself to what trajectory it is taking. Okay. I mean, it is something like you have a set of guys and girls. For every girl, there's an independent guy. But once they get married, there's a one-to-one correspondence. Okay. So basically once you have the equation of motion and you have the trajectory, it basically specifies something like which girl and which guy.
Yeah,
I
yeah.
don't know if the analogy has confused you more or clarified it.
It's fine.
Okay. I mean, in the sense that suppose instead of G and B. Now, for each of these G's, there can be one B. So they are independent before. But once they are paired, then with this one, this one, this one, this one, this one, this one, this one. So the trajectory is fixed. So once this is committed, then there is, you can, for a given G, you can find which B, and for given B, which you can find G. So then they are not independent. Similarly, case of velocity and position. Once you have given the equation of motion, each position is committed to a particular velocity. Before the equation of motion, at the level of Lagrangian, they are all independent. Every possibility is, every pairing is possible. Is that okay?
Yes.
Yes.
Okay. Okay. So now here I have got, this is my equation. And then I have d by dt of del L by del V alpha I calculate, and that gives me del by del. Okay, so alpha, this gives me E times del by del x alpha a beta dot. Anyway, so the point, okay, so so once we, just a minute. Sorry, so that will be, so it will have two portions. It will have d by dt of del L by del V alpha will have one portion from the mechanics. And this will give me something like m dv alpha by dt, the mass into acceleration. And the other portion will give me something which is electromagnetic field dependent. So when I actually substitute all this and rearrange, which I will not, which sort of is outside the scope of this particular thing, I will just give you the result. What you will have is m into d m into du alpha, yeah, m into du I, the covariant dui, by dt will be equal to E multiplied by del A k by del xi minus del AI by del xk zero ex ey ez minus ex minus ey minus ez 0 0 0 minus bz by and minus bx, and this will be bz minus by bx. You have come across this, right?
Yes.
In electrodynamics. So basically this, you basically get back your non-relativistic electromagnetic equation using this formalism. Okay. And yeah, and if you use eta ik, then the upper fik will be given by 0 minus ex minus ey minus ez ex ey ez minus bz by bz 0 minus bx, and this is 0, this is bx minus by. This is my usual electromagnetic field tensor. Okay. And if I actually, suppose I open this up, I will have m u0 is equal to E times F0 k uk, which is equal to, sorry, this should not be ds dt, but it should be, sorry, this should be ds because I'm by ds is equal to E F0 uk is equal to E times F00 U0 plus F0 alpha U alpha So this is equal to, I mean, I am doing, because alpha is 3-dimensional. English alphabets are 4-dimensional. So it is E F00. What is F00?
0.
0. Okay, so this will give me 0. Then I have F0 alpha, and the F0 alpha is Ex, Ey, Ez into U alpha. There's a mistake here, I think. Is it correct? I go take it up. Okay, so now this is so this will be equal to what? It will be equal to, now F0 alphas, upper one or minus of that. So this is equal to minus F0 alpha U alpha summation over alpha, which is equal to minus E dot V, which is correct, into E. You understand what is happening here? What is this? This is M into d by ds gamma. And what is this? Yesterday we did it, that day. What is this? This is basically the relativistic energy. If you put C equal to, if you don't put C equal to 1, it is mc square divided by 1 minus v square by c square. Is that okay? No.
Yeah, but that's here acceleration, right? Wi.
It's a W. Yeah. So it is, this is a 0 component. W0.
Yeah.
And what does it say? W0 is a change of energy. Change of energy is equal to the work done. This is force and velocity. So this is what you see, that the work done on the system is the force acted on the charged particles times velocity rate of work done on the system. So this is the energy which changes. And similarly, now you can say that m du alpha by ds is equal to E F alpha k uk, which is equal to, okay, so it is equal to E times F alpha 0 u0 plus F alpha 1 u1 plus F alpha 2 u2 plus F alpha 3 u3. Okay. Say, for example, alpha equal to 1. Then I will have E into, okay, F11 u0, and this is 0 because the diagonal term, plus, sorry, this is 0. Yeah. Sorry, no, I'm wrong. This is 1, 0. And then we have F11 u1, which is 0, plus F12 u2 plus F13 u3. And so what is this equal to? E times F10 down, which is minus Ex. No, F10 minus Ex. Minus Ex. Okay. Times U0. U0 is just gamma. Plus F11 is 0. F12. Now what is F12? F12 is minus BZ. BZ times U2, which is Vy. And then plus BZ plus By Vz. So you see, what is this? This is basically the, you understand what is this?
But that's gamma Vy, right?
Oh, yes, there's a gamma. Yeah. I'll just take that out. There's a gamma outside. Okay. Now, what is this quantity? This quantity is basically V cross B, the X component. Isn't it?
Yes.
Rather
Lorentz
minus
force.
of this. Is it okay? The X component is Vy Bz minus Vz By. And that's what you are having here, with a minus sign. Is that okay?
Yeah.
Okay. And so basically it
Yeah.
says that mass into acceleration is equal to the electric field component. Just work out the signs and so on. We can just do that. Okay. The electric field component plus V cross B, the Lorentz force. Okay. So let me not go into the details of the calculation. I think will take us away. But this is what it is. So you actually see that the relativistic equation of motion of a particle is actually this. And you get the... So it means that all the electromagnetic details are hiding in this animal called Fik. Is that all right?
Yeah.
Yes.
Okay. Now with this, you can do various things. This is a very important thing. If I have Fik, how does it transform?
Like a scalar.
Like a scalar. So it is invariant. If I substitute for Fik in this one, this will be nothing else but E square minus B square with some C factor and all that. And so you say that E square minus B square is an invariant. It's a very, very important result. And then I will come to something interesting. I had told you about the completely antisymmetric tensor. Now I can construct a tensor e to the power ijkl Fij Fkl. How does it transform?
Again a scalar.
It's a scalar, but not quite. It is a scalar only under rotation,
A pseudo
not
scalar.
under inversion. It is a pseudoscalar. Just to give you an example, so if I have V equal to V cross B. Okay. So B, okay. So for example, I'll tell you, force is a scalar, and this is equal to in Lorentz transfer, Lorentz force, it is V cross B. V is a scalar and F is a scalar. So when you invert the coordinate transformation, coordinates for odd number of coordinates, V will change sign, F will change sign, but it means B should not change sign. So a vector will change its sign when you invert the coordinates and the coordinates are odd in number. Since B does not do that, it is a pseudoscalar, and that is what you find here. It's a pseudoscalar. And if you calculate this, you will get E dot B. So let me just digress, doesn't matter in this one. I'll give you an example. Suppose I have a particle, I have a person sitting on a particle, on a charged particle. Here, E is equal to non-zero. P equal to 0. Right? Now I look at it from a frame which is moving with respect to V. Then what will happen? This will pick up an E prime at any point and it will become a B prime. But since E dot B is an invariant, then if suppose this is equal to E square, then E prime square minus B prime square will be E square because it's an invariant. You get the point?
Yeah.
Okay, it's a very interesting thing. So you can actually, okay, so yeah, this is one thing. Then there is another thing. Now I take this one. It is a pseudo-scalar, but as far as Lorentz transformation is concerned, it is behaving as a scalar. Okay, so now suppose I have a frame in which at some point I have an E like this and B like this. It means E dot B is 0. Now, if I look at it from another frame which is moving, E will change, B will change, but E prime dot B prime will remain 0. So in other words, if I have electric field and magnetic field, which is perpendicular in one frame, the direction of E might change. The direction of B might change, but they will remain mutually orthogonal, even in another Lorentz frame. Do you understand this?
Yes.
Yeah.
Okay. No, these are some interesting facts which I want to mention. The other thing is, if suppose in some appropriate units, in one frame, if E mod is greater than B mod, then whatever you may do, E may change, B may change, but the E prime mod will always remain greater than B prime mod. Because if it is not so, then this quantity will not remain an invariant. Okay?
Yes.
Okay, so these are some, I mean, there are some very interesting questions one can ask. I mean, for example, I say that, okay, I say that in one frame, I see E and B at an angle theta. If I go to another frame, if the electric field is E prime, if the magnitude of the electric field is E prime and the magnitude of magnetic field is B prime, what is theta prime? And it's very easy to calculate. Since E dot B is invariant under Lorentz transformation, I have E B cos theta is equal to E prime B prime cos theta prime, which means theta prime is equal to cos inverse of E B cos theta by E prime B prime. Is that okay?
Yes.
So I'm just illustrating some examples of how useful these invariants are. And what happens in general relativity is many times it is very cumbersome to prove it in a brute force. Using some of these clever arguments of invariance, you can actually prove things very easily. Okay. So let me just cover up this Maxwell equations. Now, we have these Maxwell's equations, which are B is equal to curl A and E is equal to minus, sorry, what am I writing? No. The definition of it. So I have this one. I have curl of E is equal to minus del B by del T. And I have divergence of B is equal to 0. And then I have another set of equations which are to do with curl B and divergence of E, which is here, just to make sure that I don't do a mistake in the sign. First pair of Maxwell equation. And the other thing is curl of B is equal to minus del E by del T plus 4 pi current density and divergence of E is equal to 4 pi charge density, right?
This is in Gaussian units, right?
Pardon?
This is in Gaussian units.
Yeah. I'm following Landau.
All right.
Okay, Landau uses these units. So, I mean, yeah, that's correct. Okay. Now, so we have already got some relativistic formulation in which we have E and B in terms of electromagnetic field density. What about J and rho? See, just like I have, okay, so I have this quantity called Ui, which is the 4 velocity. Okay. Now, when I say density, you have to be this one. So I define my rho density as just not mass per unit volume, but I go to the rest frame of the particle of the charged fluid and then define density, which means this density is a scalar because I define it as the one on the rest frame, what you can call proper density. Okay. And then I can define a quantity called Ji, which I call the forecurrent density, which is rho into Ui. Which means that J0 is equal to gamma rho and J alpha is equal to gamma rho V alpha, which in the non-relativistic limit, in the NR limit, this is rho, and in the NR limit, this is V alpha, and this is equal to my J vector, the three-dimensional current density. Is that okay?
Yes.
Yeah.
Okay. Now I use all this and the definition of Fij, and the Maxwell's equations can be written in a very cute form as the first two Maxwell's equation can be first pair of Maxwell's equations. Yeah. Can be written as, is this the one? Yeah. Okay. These Maxwell's equations can be written as del Fik by del, okay. Del Ij by del Xk. And then I have a cyclic permutation. Del Fki by del Xj plus del Fjk by del Xi is equal to 0. And the interesting thing is, if I want to write it in terms of, so since there are since ijk can take 4 values, and these are only 3 values at a time, I can have 4C3 number of combinations, which is basically 4 equations. And these 4 equations can be written in a more compact form as I, J, K, L, del F, K, L by del XK is equal to 0. So this is the form of the Maxwell's equation for the first two. The second set of Maxwell's equation can be written as del Fij by del X. I think it's J or I. Sign will be a problem. Del Xj is equal to minus 4 pi. Sorry, I'm just here. It will not matter. Here I should, it's actually written in terms of the contravariant F is equal to 4 pi Ji. So when I is 0, this becomes when I equal to 0. This basically is what? Fij, this is divergence. So it is divergence of E, right? Because F01, del F01 by del X1 plus del F02 by del X2 plus del F03 by del X3. So this is basically your electric field, right? I think with a minus sign. Yeah, these are the ones. It's a 01, 02, 03. So this portion, the zero component will just be minus divergence E. And the right side will be minus 4 pi J0, which is gamma rho. Is that okay?
Yeah.
Yeah. So I have got in the non-relativistic limit, del E is equal to 4 pi rho, which is my Maxwell's equation. In a similar way, if I take I is equal to 1, 2, 3, I will get this set of equations also. Okay. I think I'll stop with this. So basically what I have done is I have actually introduced you to the electromagnetic field tensor, which contains all the information about the electromagnetic field. I have introduced the fourth current density through which you can talk about the interaction of matter and field. Now, the reason why all this is important is in relativity in general and general relativity in particular, the source is just not mass density, but the energy density. Since the electromagnetic field also has energy, even the electromagnetic field will govern the evolution of space-time through my general relativity equations. And that is why I need to define, I need to decide how to define my field in order to define my energy of the field, which I'll come to later. Is that okay? I mean, today, it was a kind of a crash course on this one, but I couldn't help it. Essentially, I have taken portions of chapter, some portion, okay, the initial sections of the chapter 3 and portions of chapter 4 of Landau and Lifshitz, classical theory of fields. Is that okay?
Yes, Sesh.
Okay.
Sesh,
But
what
I'm
is
sorry,
the...
today it was really hurried, but I mean, I couldn't help it actually, because, if I have to do this, it will take about 10 classes, like all this in detail.
Yeah, yeah.
Yeah.
What
Any
is the
question?
dual to the field tensor?
Good. This is the one. So this quantity, na? This and this. So you can write this as del by del x k f star ij equal to 0. See, f star, or I can put f tilde, which is a dual, is equal to Eijkl fkl.
Oh,
And so since this is a constant, then the first set of Maxwell's equations, which is Eijkl del fkl by del x j is equal to 0, can be written as del f tilde ij by del x j equal to 0. And the second set of Maxwell's equation is del fij by del xj equal to 0. So the two sets, all the four Maxwell's equation can be summarized like this.
okay.
Okay, so once I know the definition of dual, okay, I can just write these are the Maxwell's equations, and from there the entire thing will come out. Now, I will just tell you here what happens. This is all in special relativity. What I will now afterwards come to in relativity is, as I already told you, the partial derivative of a tensor is not a tensor. You remember? There is an
Yes.
extra bit floating.
Yeah.
It means that these are not tensors. So I have to define a new tensor, something called covariant derivative. And the generalized Maxwell's equation in curved spacetime are Fij, I call something called covariant derivative j equal to 0, and dj Fij equal to rho. I will, yeah, no, sorry, not rho, ji. Okay, so I will come to that. Okay.
Okay, sir.
Okay, yeah. So Thursday we will not be meeting.
Hmm.
I'm going to I have to pack up my things, and tomorrow early morning I have to leave.
Mhm.
Okay, yeah. I will see you on, I am not sure about my Saturday astro thing because one of my ex-students is coming to my place. Yeah, let me see. Okay.
Thank you, sis.
Okay. Bye. Good
Good
night.
night.
Bye.
Thank you.